Okay, good morning. Any questions? So let's start from wherever we left off. We were discussing a second order effect in a MOSFET. And the second order effect that we were considering was the following. So till now, what we have assumed is our MOSFET. The incremental model of our MOSFET is this. So this is what we have been dealing with. This is what our incremental model of the MOSFET was. And if we short the source terminal incrementally, then we saw that this is GM times VGS. And then we saw that the output impedance looking in is what? In the incremental model, if I look into the drain to source terminal and try to find out the incremental output resistance, what will that be? No, how will it be 1 by GM? What will I do in order to figure out the R out? I will apply a V test, and even before that, I know the MOSFET is biased, right? The MOSFET is biased, which means that in the DC biasing picture, there is probably a DC voltage source associated with this. Correct? So if that is the case, then what should I do? Short these two terminals incrementally. And now if I look into the output, if I look between the drain and the source and try to figure out what will be R out, okay? 0, infinity, 1 over GM. Which one? Infinity. Okay. It will be infinity. Right. Because this essentially goes off, right? This essentially goes off and you are looking into the open port. And this is true in terms of our two-port network. This is true because what we have till now assumed is Y22 is equal to 0. Right? So in our case, we had Y11 equal to 0. Y12 equal to 0, Y21 was GM, which is as high as we want, right? That is a design parameter. You can size your transistor in such a way that GM is within whatever constraints you have. You can size your transistors to ensure that the GM is high with respect to something in the network. But the key point here for today's discussion is that your Y22 we consider to be 0. But as we saw so Y22 is equal to 0 means what in terms of ID VDS characteristics, that is IDS VDS characteristics. So if I see IDS VDS, which essentially means in terms of circuit picture, I am keeping my VGS same, I'm applying a VDS, and I'm observing this current IDS. And what happens if I change VDS from some small value to some large value? And our transistor characteristics in this case was something like this. And we saw that beyond this point, your IDS was saturated. That is, IDS was not changing even if you were changing VDS, which essentially made that your incremental Y parameter, in terms of incremental Y parameters, Y22 was 0, right? So in this case, Y22, which was del IDS, del VDS, was 0. And since Y22 was 0, in the incremental picture, our MOSFET was open circuited at the output terminal as far as my incremental output impedance is concerned. Okay, but then we saw in the last class that if we quickly go through what we were discussing at the back end of the last class. Your gate and source is biased, your source and drain terminals are also biased. At saturation, we assume that our channel is pinched off at the drain body junction, right? At the drain channel junction, which essentially meant that even if I increase, which meant that even if I increase this VDS, right? Even if I increase the VDS, this channel wouldn't have been affected in any way, which essentially meant that I am not influencing the channel charge. The consequence of that is we are not influencing the current, right? So that was the first order assumption that we take to that the zeroth order assumption, right? That we took while deriving this current voltage equation of your MOSFET in saturation. And that's why we came up with this equation after some mathematical jugglery. However, we saw in the last class, this is not true in the true sense of term, because even if I now increase, even if I increase the VDS, where will that extra VDS drop? That extra VDS will drop at near this pinch off region, because what will end up happening is this triangular charge configuration that you are seeing will shift slightly, right? And it will shift slightly by some, let's say, delta L. And again, to a first order approximation, you can assume this delta L to be proportional to the VDS. Whatever VDS, your extra VDS that you have applied, delta L is proportional to that. So what device modeling engineers did, they said that this seems to be, I mean, we can definitely model this, but we don't want this model to be too complicated for circuit designers, because we'll have to derive some intuition out of it. So what we did was we said that, so the simplest approximation of this effect is, I will assume that my new channel is W by L minus delta L, not L. This is the electrical length of the channel now, not the physical length of the channel. Okay, so this is, okay, so what do you think, what did I draw here? Okay, it's a potential also, but in this case, I wanted to show this is the channel charge. It's the mobile channel charge concentration, right? So if let's assume your VDS is 0 to start off, and you have applied a voltage between the gate and the source, or gate and the body, above threshold voltage, which means you have a channel charge. And in the absence of any voltage gradient, the channel charge would have been flat. It would have been a rectangular profile. Now you applied a VDS, right? That is, you applied higher voltage at the drain source, you are not tampering, which essentially means that the channel, the effective channel across, I mean, if you take any sliver of this channel and try to figure out what is the effective voltage across the channel, you will see that there will be a gradient of that effective voltage, right? So now these effective voltages, I can assume that the slivers of channels are very small individual MOSFETs, right? So each MOSFET has a channel underneath, and naturally the total charge concentration under these channels will be different, because the voltage across the oxide is different, right? Which essentially means that you will have some gradient which corresponds to the voltage gradient, some gradient of the mobile charge which corresponds to the voltage gradient. And that is what I have represented here. And what is the concept of pinch off? The concept of pinch off is, it is that value of voltage that you have applied, which essentially renders all the mobile charges to be 0 at the edge of the drain channel junction, right? So which means that beyond that, you are not able to influence the charge in the channel because there is no charge in this first order approximation or the zeroth order approximation. There is no charge to be influenced at that edge of the drain channel junction. So that is why your current gets saturated, right? So that is a zeroth order approximation. Now we are saying that what happens physically, it shouldn't make too much of, I mean, to some extent it's true, but physically, if we poke it a little further, so if I increase VDS incrementally beyond that point, what is likely to happen? That extra VDS has to drop somewhere. Where will that drop? That's the question, right? So one might argue that that drop will be okay, fine. That drop is across the entire device. So now if I probe further, what is meant by entire device? My device has multiple things. My device has an N plus part, my device has a channel charge, my device has a N plus on the source side, N plus on the drain side, and so on. So where does this extra charge drop? So as it turns out, when you are increasing this VDS, this electric field here is tending to increase, right? Since the electric field here is tending to increase, there is a overall increase in the electric field across the channel. Now, what is the effect of that? The effect of that is it cannot, since it doesn't have any channel charge just at the junction, right? What it does, it just pushes that junction slightly towards the inner side, right? If it pushes the junction slightly towards the inner side, which means this entire, now the effective channel is not L, effective channel is slightly smaller than L, right? So that essentially what I have represented here by delta L. We'll see. So as it turns out, current doesn't remain the same. To the zeroth order approximation, it remains the same. But as it turns out, because you have shortened the channel, right? You have shortened the channel. For the same VDS, if you have shortened the channel, what do you expect the current to be? It's proportional to W over L. If L decreases, current has to increase, right? So, but thankfully, this delta L is not significant. You will see why I say thankfully. So now what is happening is, yes. Okay. That's a good question. What will be the potential at L minus delta L? So why don't you tell me your thought process? So what you are saying is this voltage will be VDS, but there will be, I'm saying there is some drop across it, right? So the zeroth order approximation that we are implementing is essentially disregarding what is going to happen there. There will be a drop. Ideally, in the right model is that the moment the voltage at which you have hit pinch off, any incremental voltage that you have applied will drop across that channel, that extra delta L. So let's assume that this is VDS is equal to V overdrive and you have hit pinch off. Now you increase it further. So the extra voltage is dropping. The extra voltage should drop across the delta. Correct. Yes. Right. So, but again, that becomes if you are doing device design, then you will take those into consideration. Those extra, those gets into a second order, third order effect. So we are not getting into second order, third order effect. What we'll say is that still now, what we'll assume is, what is the best approximation that I can do by massaging this equation? Okay. So the best approximation that we are saying is, we'll not get into the details of what is happening across that small delta L, assuming that delta L is small enough, right? Then what we can do, we can simply say that the new channel is now L minus delta L, and my new MOSFET is this much. And we'll use whatever modifications this equation gives us, we'll use. Mind you, this is not an exact equation still. It's a better approximation than ignoring delta L, but still it's not a foolproof equation. Okay. So now what we'll do, we'll try to modify this term. We'll try to modify this term in a more palatable way. That is, we'll just say that this is equal to and we will further approximate it and say that this delta L is a cause of an extra voltage drop that I have applied on top of pinch of voltage, right? So ideally, this delta L should be proportional to delta VDS over V overdrive, right? Because this delta L happened because I had applied some extra voltage on top of pinch off. But what circuit designers tend to do is they say, forget about this delta VDS, we'll just replace it with VDS. Because it's in the IDVD characteristics. In the IDVD characteristics, this is my V overdrive. So you don't have any effect of delta L here, because you have not yet hit pinch off. But you have an effect of delta L after you have hit pinch off, which means that if you increase your VDS beyond V overdrive, this is supposed to increase. This is what that we expect, which means that this should be proportional to delta VDS, because I have applied an extra VDS on top of overdrive voltage. But since this delta VDS, this overdrive voltage is fairly close enough to zero, and because of modeling, ease of modeling, what we tend to do is we simply say that we will say this delta L is proportional to, assume delta L is proportional to VDS. This is again an assumption. Okay, this is not again a foolproof 100% foolproof model. This is again an assumption. If I do this, then my IDS becomes one plus some lambda VDS by L. Yes. Okay, so this is not strictly true. I think it's bothering you is that how can I replace this extra delta VDS with, how did I get rid of the delta, right? So this getting rid of delta is done to achieve a mathematical convenience. You will see why. That it's not strictly true. So you will, even if you do this, they will incur some error. But this error is, now I can say that this error is not significant because this happens fairly early in this IDVDS plot, right? So what I'm saying is, if you are somewhere over here, then it really doesn't matter too much if you are neglecting this extra, right? So, and one of the reasons you will see shortly, in a couple of minutes, you will see why that is mathematically convenient. Yes. Okay, fine. Close to zero. Yeah. Okay, fine. So now, if this is the case, then what am I? How does my Y22 change? My Y22 is del IDS, del VDS, right? It's del IDS, del VDS on top of quiescent, which means this becomes half mu n C ox by L U over whole square times. Sorry, I made a mistake here. This proportionally constant lambda includes L. So what we say is assume delta L by L proportion to lambda, and we replace this delta L by L to be lambda VDS, not this. So lambda term includes L in its expression. So that's how the literature is done. So you should also follow that. So, so now y22 is not exactly equal to 0, right? And this I can further approximate as if I say this effect of, so now, okay, so now tell me one thing, even if I move further, before I move further, if you want a transistor to behave like a current source, fair enough current source, right? It's not a good current source now. It was an ideal current source in the previous model. Now it's not a very good current source because the IDS is getting influenced by VDS. So what do you expect this lambda VDS to be with respect to 1? To be close to 1, much lesser than 1, much bigger than 1, much smaller than 1, right? Because it is only if it's much smaller than 1, you expect this slope to be quite shallow, right? Otherwise, it would have been much larger, which means that zeroth order approximation of this current can still be half mu NC of W over L V over drive square. We'll have an error, but it will not be too much. Okay. So again, for mathematical, for ease of analysis, but we still say that this is IDS times M. Okay. So otherwise, we'll have to again multiply by 1, divide by 1 by lambda VDS and do mathematical jugglery and come up with a complicated expression. That expression will be more accurate, but you will not get too much information from that expression. So since you cannot get too much information from the expression, you just said that forget about it. Will not get bogged down with things that don't matter too much. Okay, so your y22 becomes lambda time IDS. Okay, so this is one of the reasons. The fact that we can do this is because we replace this delta VDS with VDS, right? So once if we had kept delta VDS, right, then we would have had to come up with an extra V over drive term, and that would have made this expression of y22 slightly more complicated, right? So your y22 now is fairly simple because you have to do ultimately some analysis and figure out how the device behaves. So y22 expression is fairly simple. It's proportional to the quiescent current that is flowing through it, assuming that quiescent current is independent of VDS, right? If you have to find out the quiescent current, the way to find out I22 is you find out the quiescent current, assuming that there is no effect of lambda, VDS, and all, and then multiply it with lambda, and whatever you get is equal to your y22. Okay. Yes, you had a question. Okay. So because that model is not accurate enough, because your transistor actually doesn't behave like an ideal current source. All of them are valid, but there will be slight modification for each of them. Okay, we'll see that. We'll see how it affects your overall design. Okay. So that's how, I mean, we have not come up to this point in the course to say everything what you have done is null and void. We'll again restart, right? So that's not going to happen. Okay, fine. So now, if this is the case, okay, so there is another, just like y21 we call as GM. So this y22 in case of a transistor is called GDS. The conductance between drain and source. This is also called 1 over RDS. Resistance between drain and source, right? So you will see these terms in the literature quite often. So now, what does by the way, before I proceed, one more piece of jargon. This effect of reduction of channel because you have applied some extra VDS is called channel length modulation. Okay, so this effect of or abbreviated as CLM. So often you will hear people say that sometimes you neglect CLM, sometimes you don't. So CLM would essentially mean that we are neglecting whether we are, the statement will essentially mean whether can we neglect Y22 or whether we cannot, right? Yes. Right. So how was channel flowing at when we were not considering channel length modulation? There was still at that junction, there was still no channel, right? So if you go back to that lecture where we talked about it, even though there was no channel, there was an electric field, right? So you had, so charges were available, the mobile charges were available in the channel everywhere, but for that junction. So now if the charges are available just at the edge and you still have electric field, the charges tend to be sucked in through that electric field. This is equivalent to a PN junction where you have a reverse saturation current. So if you have in a PN junction, when in the depletion region, when you had electrons and holes getting generated, they were sucked into the P and the N side, which was giving rise to some reverse saturation current in a PN junction, right? So the concept is similar here, just that the charges are not getting generated by thermal effects. The charges are provided by an adjacent channel, a channel which is just next to that pinch off region. Since you have charges are available very close to the channel and you have electric field penetrating that channel, so the charges are getting sucked in. So one obvious question is, since the current is flowing, there is mobile charge there. Has to be. And that is accurate. There has to be mobile charge there. But when we say if we don't have any charge, we have some charge, it is always with respect to some background. Here, when we say that we don't have any charge, which means we have much lesser mobile charges with respect to the background ionized impurities that are there, right? So when you have P minus, when the body is P and you have applied VGS or VGB, what the first thing that happens is you deplete all the holes and you get some ionized impurities, which are unmasked, right? So you'll have Na minus, immobile charges that will get unmasked first. Then if you keep on applying incremental, if you keep on applying higher VGS on top of whatever you started off with, you will see mobile charges, right? So that essential concept was that of threshold voltage, right? So now what we are saying is, if we increase this VDS, the incremental, the small sliver of MOSFET that we are seeing around that drain source junction is getting depleted even further, but we still have electric field through it. And since the adjacent MOSFET, that is the adjacent sliver, has some mobile charges, I'll be able to pull those charges through the depleted MOSFET, right? But the charge that I will be seeing will be much lesser than Na minus. That's why we are saying that effectively the terminology says that there is no mobile charges. But sure, if you have current flow, there should be mobile charges. But that mobile charge has not been generated by the application of VGS. That's all. Okay, so the mobile charges is okay. Now, so that answer to that, his question is, looks like charges are decreasing, then why is current increasing? Fair enough question, right? So the answer to that is here. You don't have to go to the pinch off. You consider this sliver of MOSFET, you consider this sliver of MOSFET. Are the charges same? But current is same. Why? So, yes, potential is different. So, I'll give you a different context, which you are, I think, more comfortable with. When you see fluid mechanics, it's KCL, right? Yes, but how do you answer this question? Pardon? Yeah, exactly. The rate of flow will be different. It's like a tapered pipe, right? So the velocity will A1 V1 equal to A2 V2 essentially, right? Exactly. Your velocity will be different. Okay. Yes. Can you repeat the question? Surface charge. Why do you say that? Right. No, actually, okay. So this is getting deep into device physics. As it turns out, it doesn't depend on that. Okay. So in 311, you will see that because of another effect, which we cannot go into this class, beyond when you apply a VGS on top of a certain threshold, so the rate at which your mobile, the charge density will increase, it almost logarithmic. That is, it goes very slowly. Okay, so unfortunately, we cannot go there in this course, right? So it doesn't. It more for all practical purposes, you can assume that the charge density remains as is, right? It doesn't get affected too much with respect to VDS. But you can see that the slope has changed. So essentially, you can relate this extra charge, extra current by the change in slope. Okay, fine. So now what is the effect of how does our incremental model change? Our incremental model gets shifted to, this was my incremental model initially. So now this is the old model. This is GM times VGS. My updated model is this. Right, where TDS is lambda IDS. Okay, so now can you tell me how does all your circuit analysis change? Does it change any way? I mean, as far as the analysis part is concerned? Pardon? Right. So exactly. So it's in terms of incremental model, all you have to do is apply a resistor across the drain and source terminals. Nothing else changes. Okay. So whatever you have done till now is valid, but with an extra addendum. The addendum is there will be a extra resistance between the drain and the source terminals. Okay. So, pardon? That okay. Value of GM will change because there is an extra 1 plus lambda VDS term, right? Yeah, good observation. So his point is my ID is half Newman Cox W over L. My GM is delta ID del VGS, which is embedded here, right? So this is so GM expression seems to have changed, but again, simplify. We said that this is almost equal to right. So we'll get some error definitely, but that error is not significant because this lambda VDS is much less than 1. Okay, so you'll get some error in GM definitely, But what we are saying is that we can neglect that either, because if something is much lesser than 1, I can neglect that with respect to 1. But in case of GDS, we cannot do that because nothing can be much lesser than 0, right? When you don't have a GDS and you have some GDS, these are completely different scenarios. You will have infinite error if you neglect GDS when you are supposed to have some. But in this case, the percentage of error is not significant. So we'll still go with the old expression of GM, right? So that's what this incremental model helps us do. When moment you are stepping into the incremental zone, you are saying that I am okay with some error because I'm neglecting higher order terms. Then the question now becomes, how much more can I neglect? And as it turns out, you can do a lot of these approximations based on scenarios. Yes. Yes. You can. I didn't understand the question fully. Yeah. Right. Okay. So, so the moot point is that whatever you have done till now, everything is valid. Your GM expression is still the same, approximately, but all you have to do is add an extra resistor, extra incremental resistor. This is not a physical resistor. This, just like a GM is not a physical current source, you have an incremental resistor between the drain and the source terminals. Now, what is the effect of this? If I go back to our common source amplifier, so you have applied some EGQ, and on top of that, you have applied some PI. So what will be the incremental model of this, taking into account GDS? Yes. So this is lambda VDS is much lesser than 1. That's the only reason we have neglected it in the calculation of GM. But you cannot neglect that in the calculation of GDS because with respect to 0, you cannot neglect it. Okay, so now how will our incremental model change? You do the same thing, just the transistor model has gotten changed slightly, right? So so this is gate, source, drain. So our incrementally, my transistor is this. You have GDS, you have GM, BI, and you have RL. So earlier the GDS was not there, now you have a GDS. So how will your analysis change? What will be V0 over Vi? Note that these are grounds, right? All the grounds are connected. So what will be V0 over Vi? Exactly, right? So you'll get minus GM times RL parallel RDS. Okay. Which means I can write it in this form also. GL plus RDS. Okay, so this is as far as the mathematical expression is concerned, which is pretty simple, but there is a profound effect of this GDS. And the profound effect is the following. In the common source amplifier question that you had done till now, what you had assumed is if I have infinite VDD available to me, right? You could have gotten an infinite gain, right? So you keep on increasing RL, for the same GM, and which means that my gain was GM times RL. If I keep increasing RL, the drop across RL will increase, and to accommodate that drop, I have to increase VDD. But in principle, in theory, I could have gotten infinite gain by playing that game. But now can I get that? What is this model telling us? It is limited by its transistor's own characteristics. So there is a maximum gain that you can get out of a real transistor. You cannot get infinity. Just because you have loaded the output with an infinite resistance doesn't mean that you'll get an infinite. Even theoretically, you will not get an infinite gain. Okay. So how much gain you will get? What is the maximum gain that you can get now? Minus GMRDS, right? So my V0 over Vi max is minus GM by GDS. Okay. And the key thing about this is if I replace this GM and GDS with respect to the quiescent parameters, then GM is and GDS is lambda ID, right? So this is proportional to 1 by square root ID. So what this is telling you is, if you want to increase the gain of the transistor, the self gain of the transistor, that is the gain that you get when you assume that load is infinite, the pure gain of the transistor, it is inversely proportional to square root of ID. So if you ideally, in order to get a better and better transistor, you would like to get GDS as close to 0 as possible. Right? A best transistor is the case where if GDS is 0. That is an ideal current source scenario. But in the absence of that, you would like to ensure that GDS is as close to 0 as possible. And if you have to achieve that, what is this expression telling you? You'll have to bias the transistor with smaller and smaller current. If you increase the current, your GM will increase definitely, but so will your GDS. And the rate at which GDS increases is higher than the rate at which your GM increases. Your GM is proportional to square root of I. Your GDS is proportional to I. Right? So the self gain of the transistor is decreasing if you increase the bias current. Yes. Okay, so because of okay, so as I said, you increase VDD, you have unlimited availability of increasing VDD. So even then you will not be able to hit, right? You will not be able to hit infinite gain because it will be limited by GM by GDS of the transistor. Yes. You can potentially, if you can increase VDD, right? You have to, you have to accommodate for that. Otherwise, it will go into linear that we saw, right? So this term GM over GDS is called the intrinsic gain of the transistor. Okay. So today's course has more jargons than usual, but this is something that you'll have to deal with. So essentially, ideally, you would like to have this intrinsic gain of the transistor to go to infinity. That is, it is not loaded by its own GDS, but you will not be. You cannot hope to do that because everything is real. So you'll have some GDS, which means that you'll have to ensure your transistor GDS is as low as possible, or in other words, the intrinsic gain of the transistor, that is the maximum gain that you can get out of the transistor, should be as high as possible. Right? If it is not, then your gain will be limited by the intrinsic gain of the transistor, regardless of whatever R you apply, whatever R you are trying to drive. Okay. One more important observation: is lambda a design parameter, or is lambda a device parameter that you cannot do anything about it? Yes. Exactly, right? So your lambda is delta L by L. Delta L, you cannot do anything because it depends on how the device is, how much the channel will move, right? Delta L, you cannot do anything, but L is a design parameter. Okay, how did I express that? Correct. Lambda times VDS is delta L by L, right? No. I don't think that is correct, right? Yeah, lambda VDS is delta L by L, correct. So your lambda times VDS is delta L by L, which means your lambda is delta L over times VDS. VDS you have for a fixed VDS we are talking about. So, and delta L you cannot change. So essentially this is proportional to 1 over L. And you would want to get high value of lambda or low value of lambda if you want to get higher intrinsic gain. If you want to make a better transistor, low value of lambda. I should be able to neglect that lambda VDS term, right? So as a designer, if you, let's say you have designed a common source amplifier and you found that your GM by GDS is 10 or 20 or 100 or whatever, and you want to increase it further, what will you do? What will you do? You have to increase L. Right? If you increase L, your GDS, your lambda decreases, which means your GDS decreases, which means so if you increase L, implies GDS goes down. Exactly. It will affect the current, right? My current is proportional to W by L. So my IDS is proportional to W by L. So I cannot unilaterally increase L. It will affect the current, it will affect GM. Let's say I do not want to affect the current, then what should I do? But I still want this effect. You also have to increase W, right? So, which means also need to increase W to keep IDS and GM unaffected. Okay. Now, as it turns out, now let me give you some numbers. In a standard, let's say 130 nanometer technology, but which when I say 130 nanometer or anything, what I'm essentially saying is I'm quoting the length of the channel. That's how a technology is quoted, the technology node. So in a 130 nanometer technology, this ratio of GM over GDS for L equal to 130 nanometer. This is approximately, obviously this will change. This can again be affected because of many other design parameters. You get approximately 10. In case of 65 nanometer, you get about 5. This is when L is 65 nanometer or 60 nanometer of that ballpark range. Again, these are not sacrosanct numbers. These can change, but this is a ballpark range. You should have an estimate. So let's assume that I have designed a circuit. I have designed a common source amplifier, and I find that the output. So what I'm getting at here is, let's say you have hooked up a circuit. And let's say you have figured out that you have biased it with certain current, and you know that GM is 1 millisiemens. Okay. And let's say this is, or GM is 10 millisiemens, let's say. And your RL is 10K. And you have biased VDD in such a way that transistor is in saturation. And we observe V0 over Vi is approximately 20. What am I expecting? When you are designing, you start off with the design of expectation. That's how I figured out the That's how I put these numbers. What am I expecting in case of an ideal transistor? Which means approximately 100. We are expecting 100, but you hooked it up, you put it in a simulator, or you have checked in a breadboard, and you see you will get this. So what do you think is the culprit? It's the GDS, right? So it's the GDS that is the culprit. So essentially, in the incremental sense, you have a GDS. Okay, or RDS, if you're comfortable with that. So all the incremental current will flow into RDS and not go into RL. Or in other words, you can say that RDS parallel RL is approximately equal to RDS. And from this observation, can you tell me what is approximately the value of RDS? You did an experiment and you found this. Can you tell me what is the approximate value of RDS? Pardon? 2 kilo, right? Because it is only when 10 millisiemens gets multiplied by 2, you get minus 20, right? So this is approximately 2 kilo. Okay. And let's say I still want minus 100. So what design change will you do? Pardon? And how will you increase RDS? RDS, it's not a physical resistor. You have to do some change to the device to change the RDS. I don't want to affect GM, but I want to increase RDS. What will I do? We just discussed. We'll decrease lambda. How can I decrease lambda? I can only change W and L, right? I have to increase L and I have to increase W, right? So you have to increase L by how many times? You started off with some L. Initially started off with W by L. How many times do you have to increase L in order to get to RDS is more than 10K? 5 times at least. If you get to 5 times, you will get a gain of minus 50. But let's say you increase it by 10 times. You increase L by 10x. But you want to keep GM to be same, current to be same, which means you have to increase W also by 10. And that's how you design, right? You hook it up in some way, and then you see, you expect something, you observe something, and then you go and figure out what might have gone wrong. From whatever we have seen till now, looks like GDS is the culprit. I have to change GDS, but I don't want to change anything else. So we increase L, and then we increase W also. Consequently, obviously, you see the area of the transistor has gone up by a factor of 100, right? The physical W and physical L you have increased. So area of the transistor has gone up by a factor of 100, which is the design cost. Okay, there are ways of getting around that. We'll see that when time comes. Okay, let's stop here.